Okay, so if light goes into glass and bends towards the normal, that makes glass kind of a problem because it's distorting light. But one of the things, most of the ways we're using glass is as windows. Think of that. If, let's draw this glass, there's one side, here's the other side. So we have an angle of incidence, we have an angle of refraction. But now, when it comes out the other side of that pane of glass, we have a new problem. And remember how I said it was symmetric? Well, if this is the new angle of incidence, the angle of refraction is going to be that. It's going to bend away from the normal when it comes out into air. So here's glass, here's air, here's air. So actually it has shifted a little bit, but this line would be parallel to this. So when we have thin panes of glass, it shifts a little bit. Every time you're looking through a pane of glass at an angle, you're seeing an image that's a little off from where it was, but it doesn't bend it a lot. Prisms bend it a lot because these two sides are not parallel, so light actually goes out in a completely different direction. Now let's take a look at a consequence, a weird consequence of Snell's law, and two materials, and let's have light going from a slow material to a fast material. Slow, and let me just say n equals 2, so it's half as fast. And here's air, so n equals 1. Okay, and what I'm going to do is I'm going to send light out at an angle of 30 degrees, and I want to see what happens when it gets into air. And so I do my equation, n1 sine theta 1. I can pick any material to be the first one, n2 sine theta 2. But what I'm going to do is I'm going to do the slow one. Okay, so 2 sine of 30 equals 1 sine of, and we know it's going to move away from the normal, 1 sine of theta 2. So when we do that 2 times sine of 30 divided by 1, is 1. Sine of theta 2 is 1. I accidentally came up with what's called the critical angle. Critical angle is the point where, well, sine of theta 2, what would theta 2 be to get a sine of 1? It would be 90 degrees. Theta is 90 degrees. What does that mean? That means the light bends so far away, it bends along the surface. It really doesn't do that. Okay? If I had this the least bit larger, this would be greater than 1. There would be no solution to this equation. What does that mean? If there's no solution to that equation, that means light can't escape. That means all of the light would reflect. Remember that some light is going to reflect, some is going to refract, but if it can't refract, it's all going to reflect. So if this side is greater than or equal to 1, we have what's called total internal reflection. And this point where it's exactly equal to 1, that's the critical angle. I shouldn't say that, because that's not the critical angle. That's the case of the critical angle. That makes this the critical angle. When n times the sine of an angle is 1, that means light's not going to be able to escape anymore. If the angle's any bigger, it'll all reflect. And so we call that the critical angle. How do you solve for the critical angle? Set this side equal to 1. Say this is 90 degrees times 1. And then you can solve for the critical angle if that's an unknown. That's a little beyond what we're going to be doing in this class, but I just want to show you how that would happen. So total internal reflection, who cares? Why? Why would I care about that? If you've ever looked at a fish tank and there's certain angles you can't see certain parts and you're trying to go around and you see it, that's based on total internal reflection. And in fact, fiber optics, if you have Verizon Fios, That's based on total internal reflection. What happens is you have a tube, a glass tube, and that glass tube, you put light in at the end. You send light in at the end, and light can carry information. And that light comes here, and it's at such a big angle, it can't refract, so it all reflects. And it comes down here, same thing happens, okay? This angle is so big, there's no refraction, total internal reflection. And it just keeps bouncing around like this. And so fiber optic systems are based on sending information carried on a light beam and putting it through a glass fiber in a way that the light doesn't escape. So it's very good at transmitting energy efficiently with very low losses in the middle. And that's total internal reflection.